This is Mrs. Palmer-Quag with the first video for Module 14. This module is on kinetics, and in this video I want to talk about the factors that affect reaction rates. First, a little review. There are two driving factors that cause chemical reactions that we've been talking about in the thermodynamics module. Those factors are a decrease in enthalpy, or a negative delta H, a lowering of the energy of the products as compared to the reactants, and an increase in entropy, which is also known as disorder, and we write that as a delta S. If a reaction occurs, it is known as a spontaneous reaction, and spontaneous reactions are driven by these two factors, enthalpy and entropy. If both of these driving factors are present, going in the correct direction, lower energy, more disorder, then the reaction is spontaneous at all temperatures. If only one is present, the reaction can occur, but it's dependent upon the temperature to make it happen. If neither is present, the reaction is not spontaneous and will not occur. So in kinetics, we are concerned with spontaneous reactions and how fast those spontaneous reactions will occur. Remember, just because something's spontaneous doesn't mean it's going to happen in a hurry. Combustion of wood is a spontaneous reaction, and it does happen fairly quickly, but so is the rusting of your car. And you know that that is a very slow process. Good thing it doesn't happen as fast as burning a campfire, or we'd never be able to get anywhere in our cars. So when we talk about the kinetics of a reaction, we're going to be talking about the reaction rate. And this is a mathematical expression that shows the change in the amount of the product over time. You can also have a reaction rate as expressed as the negative of the change of the amount of reactant as well. But most often we're talking about product. So this graph down here is a hypothetical reaction. Our blue line is our product. And of course it will increase over time. You can see that it starts down here at 0, and then after 25 seconds we're looking like we're about at 0.7 or so at this endpoint on the graph. And as the product increase, as you would expect, your reactants, which are here as your red line, will be decreasing because the reactants are being turned into products. So as the product line goes up on the graph, as the amount of products increases, the amount of reactants decreases. Now to determine the rate, you want to look at any 2 points. So if we start here and compare what happens to the rate between 0 seconds and 5 seconds, we want to look at the amount of product that is made at both of those points. So obviously we started with no product because we're just combining our reactants, and so our products would go from a final point of molarity of 0.3 minus the initial molarity of 0, so it's not going to be changing, you don't have to put a number in for there, over a time of 5 seconds. And so if we divided that out, we would find that we had a reaction rate of 0.6 molar per second as the, or 0.06, sorry, I need another 0 there, 0.06 molar per second as the reaction rate. So in order to figure out a particular reaction rate, you always have to have 2 points to compare as what's happening in the change of products over that particular time. You will notice that, especially with the reactants, there is a change in the slope of the line as this reaction progresses, and that goes on. The reason that happens is correlated to a theory that's not covered by the book that helps explain why reactions happen, which is called collision theory. So I want to talk a little bit about collision theory in the next slide. So in collision theory, we picture these reactions happening because chemical molecules are bumping into each other. And the reactants are able to form products only when they collide with sufficient energy as they bump into each other, and in the correct orientation, the correct arrangement, so that they can have old bonds broken and new bonds form. If there's not a collision, there won't be a reaction, and if there's not a collision that has enough oomph and in the right manner, it's not going to happen either. So if we take this reaction here where you have nitrogen trioxide mixing with carbon monoxide to give you nitrogen dioxide and carbon dioxide, we've got 3 potential ways this reaction could occur. In this first one, the reactants are moving too slowly, and so the molecules just bounce off each other. And this is known as an ineffective collision. Nothing happens. There's not enough energy for them when they run into each other that they're going to stick together and do anything. In the second illustration down here, the reactants are not facing the right way. So they bump into each other, but the bonds that have to break and reform are not next to each other. So again, there's no reaction. But in this third diagram, we have both enough energy and the molecules oriented in the correct fashion so that they can bound together and break the bonds and make new bonds to have the chemical reaction. So this would be an effective reaction. So reaction rates are dependent upon effective collisions. And in order to increase the effective collisions that happen in a chemical reaction, there are several things that will improve your chances. The first one is to increase the concentration of the reactants. That if you just think about it, that makes sense. If you have lower concentrations, fewer molecules to bounce into each other, then you're logically going to have fewer collisions. It's like, trying to work your way through a crowded room as compared to walking across an empty room or a very sparsely populated room. Of course, you're going to likely to run into more people when it's in high concentration. So a greater concentration of reactants then leads to a faster reaction rate. And that's why if you go back to that thinking about that little diagram where we saw the hypothetical situation, our reactants were coming down, the slope was decreasing quite quickly, and then it was leveling off because the concentration of the reactants is also decreasing, so it's slowing down their rate, and the slope of the line is becoming more horizontal and less vertical. If your reactants are gases, you can also increase the concentration by increasing the pressure because you'll be squashing those molecules closer together and effectively then increasing the concentration, the number of molecules per unit of area. Another way to increase your reaction rate, increase your number of effective collisions, is by increasing the temperature. And that directly impacts on the energy. So we have these little diagrams trying to show that these blue molecules don't have as much energy as my red molecules who have been heated up. And of course, temperature is a measure of the average kinetic energy. Kinetic energy has to do with motion. So molecules that have a higher kinetic energy are moving faster, they're moving harder. When they collide, they're going to collide with lots of energy behind it, and that increases the chance of having an effective collision with enough energy to cause the bonds to break that start that whole reaction. 2 other things that influence reaction rate are the surface area. Increasing the surface area of a substance increases the amount of substance that is available to react. So we've just sort of got a graphic illustration of this first one in A. We've got something trying to react on a big lump of metal. Let's pretend this is magnesium here, this blue lump, and hydrogen is trying to react with it, and it can react around the outer surface of the lump of metal, but it can't get into the inside. But if you powder it, then you're going to make lots and lots of places where the hydrogen can attach to the magnesium, and you'll get a good reaction. If you've ever used the hand warmers that you have a plastic package and you unpack it and it's sort of a cloth wrapped pouch inside and exposure to air, those will warm up in your hands, those hand warmers. Well, they're actually made out of iron powder. And so what you're having happen is rusting is going on inside that package. When you take it out of the plastic, it's being exposed to air, and oxygen is reacting with the iron. And because the iron is like this diagram B over here, it's in tiny, tiny, tiny pieces, the reaction happens much more quickly than it does the rusting that would happen on your car. It's the same process, but the surface area makes a huge difference of the reaction rate. And then the final thing that will influence reaction rates is the presence of a catalyst. And so the catalyst is some other compound that will bring the 2 reactants together and encourage the bonds to break and new bonds to form, and encourage the reaction to happen. All of the things that go on in our body happen because there are catalysts, protein catalysts known as enzymes, that allow them to happen. because this energy diagram shows you graphically what happens with a catalyst. Under normal conditions, this reaction requires this much activation energy to get started, and that's a whole lot. But when you put a catalyst in, you only need a tiny bit of activation energy for it to happen. If you've ever fooled around with Mentos and Diet Coke, the Mentos are acting as a catalyst to release the carbon dioxide from the Diet Coke. It doesn't have anything to do with the Mentos candy itself. It's just how the candy is formed. It has many, many tiny little pits on the surface, and that encourages the carbon dioxide to come out of the solution, and then, of course, make your diet soda erupt most spectacularly. And so the activation energy has been greatly lowered by the presence of that catalyst, leading to a very spectacular reaction. I want to tell you a few more things about reaction rates. These are not covered by our book, so you just count this as bonus information. But as you could suspect, the fewer number of electrons that have to be rearranged with bonds, the faster the reaction is going to occur. So ionic substances in aqueous solutions tend to react quickly. And if you think about it, a lot of our chemical reactions that we do in chemistry lab involve ionic substances just for this very reason. We have an hour to get through lab. We need to have something happen in front of you, so I need to pick chemicals that are going to do something in a hurry. Covalent substances, in contrast, react much more slowly without a catalyst, almost impossible to detect sometimes reacting at room temperature, and so that's why catalysts are so important in our human body reactions. In more complicated reactions where you have more than two reactants, then several steps are going to be involved because it's highly unlikely that three things are going to bounce together all at the same time with sufficient energy and in the right orientation to make a new product. It's much more likely that part A and B will bounce together, and then B and C can come together, and then you end up with product D. And so there are a series of steps involved in reactions that have more than two reactants. And we call these series of steps a reaction mechanism. The individual steps within the reaction mechanism might be fast or slow, and so whatever is slowest becomes known as the rate determining step. It's like the weakest link. The slowest step is going to determine the final reaction rate, and so it's increasing the concentration of substances involved in this step that will increase the reaction rate. If you change the concentration of the substances that are involved in a fast step, but you don't do anything about the stuff involved in the slow step, it's not going to change the overall reaction. So this is just a little bit of extra information not included in your textbook to sort of round out this discussion of reaction, the factors affecting reaction rates.